Hello, I'm Jeffrey Fox. I'm going to tell you about something pretty exciting. The new Department of Intelligent Systems Engineering at Indiana University Bloomington, which is part of the School of Informatics and Computing. So this is a small, relative, compared to other engineering schools or colleges, this is pretty small, maybe 25 to 30 faculty in 3 to 4 years. And it's pretty focused. It does not have, say, as many subunits as other engineering colleges, but it's pretty exciting because it's Indiana University's first formal entry into engineering. We're expecting to have, 4 or 5 years from now, around 500 undergraduates, 200 master's students, and 125 PhD students. The motivations of this department being set up were multiple. One of the major motivations is that almost all other large-scale universities like Indiana have engineering curriculum. But more formally, there was an economic development report by Battelle, which was funded by the Lilly Endowment, and it explicitly recommended that IU form an engineering program partly to help economic development in the state south of Indiana. We also have very strong programs in computer science, informatics, biology, chemistry, environmental science, physics, and psychology and brain science, PBS, and those will be strengthened by engineering offerings and vice versa. Now, this was only approved actually less than a year ago, August 13th, 2015, and so that we're now coming to the formal actual entry of new students, but those new students, we didn't have much time to tell them about it, so we're having rather modest enrollments compared to, again, our peers. But we expect to have significantly higher enrollments next year because we have, starting now, much more time to properly advertise it and talk to high school counselors and things like that. So this picture on the slide tries to show the structure of ISE, and this was actually part of came from the motivating material for the department. We have sort of 6 concentrations: bioengineering, computer engineering, cyber-physical systems, which some people might call the Internet of Things, environmental engineering, molecular and nanoscale engineering, which is effectively nanoengineering, and neuroengineering. So those are 6 concentrations. We don't offer those at all levels or degrees. And they are sort of integrated by a focus on things that are small: sensors, detectors, instruments, mobile devices, robotics, computing hardware, which FPGAs and things like that. Now, we have some sort of core things that feed into this. One is the concept of an intelligent system. If you're an engineer, you might build some hardware and deploy it. That hardware usually has lots of signal processing done on it, and the data taken by that hardware is converted to information. Then the intelligent system comes along, which today might even involve deep learning, and it converts that information to knowledge and wisdom and decisions. And so a key aspect of this curriculum is, both at all levels, undergraduate, master's, and PhD, is that we're focusing on end-to-end engineering, from building the hardware, designing the system, deploying it, and then taking that data, correcting it to make it information, and then really drawing decisions from it in sophisticated ways. And so intelligent systems, cloud computing to support that, machine learning and everything is a key part of our curriculum at both the undergraduate and graduate level. Another key part is high-performance computing, modeling and simulation, as well as user interface design. And so there will be components of the curricula in these areas, which makes it a little different from some engineering programs. We will, of course, cover the core of much engineering: signal processing, control theory, and information theory. So what about the structure? Well, I've already pointed out the department in the School of Informatics and Computing, and it may well have faculty appointments, which are both in the department and possibly joint. And those joint could either be with other units, other departments in the school, or with other units on campus, because there are many departments on campus where we have natural collaborations, chemistry, biology, physics, psychology and brain science, environmental science, which is SPEAR, and we expect, though we don't have any joint appointments at the moment, we expect that to happen. We're going to eventually move to the 4th floor of the new Luddy building for the school, but we will also have most of our major research in what's called ISAT, which is originally the cyclotron building on the bypass. And later we will discuss the faculty, the undergraduate program and the PhD program. We also need to work closely with everybody, and so we have the concept of a collaboratory, which is an organization that will help us partner with industry and actually the other faculty on campus. At the moment, we have an approved PhD and undergraduate program we'll discuss. We will submit the master's proposal during this academic year, which is actually just starting. Well, we'll start in maybe a week and a half. And we hope to offer master's degrees for students entering in fall of 2018. We don't actually know quite how that will look yet. There is no doubt we'll want a master's in computer engineering and cyber-physical systems, because we know from our experience with other related programs in the school that's very popular. The other concentrations may not need a professional master's program. We'll need to make that decision later. So we've already discussed that intelligent systems is not a sort of random name. It's been carefully thought through, because systems actually take data, convert to information, and make that knowledge, which is a well-known pipeline. And we're going to support fully that pipeline. And examples, which I sometimes give traditional engineering departments, they'll tell you how to build a car or build a building. In intelligent systems engineering, we'll tell you how to put the sensors in that car and they do the software to make self-driving cars, and when for the building, we'll tell you how to build the sensors that detects the earthquake and tells you how the building is responding to it. So that's why we have to do machine learning and clouds as part of our curriculum. So cyber-physical systems, there are a few programs starting in this area around the country. So we're not the first, but we're one of the first to offer a full curriculum in that area. And that includes robotics, it includes the Internet of Things. And if you read the literature, almost every day there's a news article about the Internet of Things and whether there's a security flaw making it impossible to work, or just why it's being adopted by industry. And the usual way to think about the Internet of Things is smart X, where X can be a train, a car, a city, a house, or what have you, or in the case of industry, or the refrigerators and air conditioners and what have you, they're all now smart. They have sensors which are sending their data back actually effectively to a cloud, and then they're getting processed. And it's well known that if you listen to talks from General Electric, they will point out that their engines send back, which have sensors of course in them, and their aircraft engines send more data back to GE Central than Twitter produces across the world today. So that's a non-trivial amount of information. So that's the type of thing we're doing. Again, we're not teaching students to build aircraft engines, although that's pretty important. We're teaching them about the sensors that will tell you when the engines are performing well or not so well. And the important issue to realize is that modeling and simulation is an important part of many engineering fields, because you can now simulate, due to high-performance computing, many important things. Again, you can simulate cars, you can simulate buildings, you can simulate maybe one of our faculty works on things like virtual tissue. You can simulate the body, and large-scale using high-performance computing will be a major part of this curriculum, this research and curriculum. Say we will teach students to do that. And we have to actually develop those modules. I should also point out, I forgot to mention one of the more important examples is nanoengineering. A lot of that is new materials, material science, and that all involves material science is heavily founded on being able to simulate new materials and see from the simulations before you do the experiments what actually might work. All right, now let's come to the various degrees. We'll start with the undergraduate degree, a Bachelor's of Science in Intelligent Systems Engineering, and it will be accredited under ABET. And we have rather ambitious plans here, but initially, given the few number of faculty we were starting with and the difficulty of getting all this done, starting August 13, 2015, we're only offering 2 initial tracks, one in computer engineering and one in cyber physical systems, which actually have the first 2 years in common of the 4-year degree, and the last 2 years are distinct. So the core, these degrees are pretty intensive. Currently, they have 45 credits in the core, which is taken by both CE and CPS students. And that will actually cover intelligent systems and modeling and simulation, as I discussed. That will be taught to all our students. Then there'll be 6 credits of electives, 18 credits which are track-specific, and then there are the 21 credits of general education and 30 credits of math science. And we will try very hard to put in opportunities for entrepreneurship, research, and internships with industry. That's one reason we need to build the industry partnership, so we have these internships waiting for our students to work on, and not just when they leave IU, but during their education here. I should say that we designed our curriculum so it is competitive in technical depth with all the other major universities, both in the state and nationally. And it is a little different focus, probably compared to other programs. It has less on electrical engineering and more on cyber physical systems. So it's different, but we believe we've chosen technical foci, which are actually probably more important than maybe some of the ones being done in other universities. Only key feature is that the total number of units is still 120. And whereas if you go to many engineering degrees at the curricula at other universities, you'll find 128, 132 unit curricula. So cyber physical systems, we really haven't designed that because that track, although there's some introduction in the second year, that track only really starts in year 3, so we don't actually have to have it fully designed yet. That needs a little bit of thought. We will certainly cover robotics, but what else we cover, I say there are some emerging degrees at other universities where we've studied a lot of them, and we will make our decisions probably this year about how CPS will look in detail. We do hope to add other focus areas or concentrations both in the bioengineering area and nanoengineering area. Exactly how we do that is still being discussed because we won't have enough faculty to offer a full bioengineering degree, say similar to that at MIT, Berkeley, Purdue, Ohio State, and what have you. So exactly how that specialization looks needs to be discussed. Our computer engineering and CPS will be competitive with the other universities. We have around a little more than 20 undergraduate students enrolling in the program this year. And we have in their first year, they will have general courses from the university like physics, and they will have 3 Pacific Intelligent Systems Engineering courses, instruction and innovation and design, computer architecture, and computer programming. All right, now we come to the PhD, where we actually have actually 18 students at the moment, 15 new students and 3 transfers from computer science. And we already offer 6 tracks. We can do more tracks at the PhD level because the PhD has less courses needed, and we have mainly to support the research, and we have enough faculty to get started in research in all the 6 tracks. And so this PhD could be taken by students with a master's in engineering, or maybe in, say, biology-related field or in the IT field. We're really going to focus on research excellence and probably not so much at the courses at the PhD level, because it will take us a while to build up a rich set of courses. But we expect our students to be mainly supported on research grants, research assistant positions on grants. So this entering class has 3 CS transfers, 5 computer engineering. 1 is a part-time student from Crane, the Navy base just south of Indiana University, 6 in cyber-physical systems, and then 1 each in bio, nano, neuro, and environmental engineering. So all 6 tracks are represented in our first year. Now let's just go through the faculty. There are 4 what you might call founding faculty. Myself, my area of expertise is big data and parallel computing, and also cyber-physical systems. There is James Glazier, who transferred from physics. He is in bioengineering and biocomplexity. I already mentioned his exciting work on virtual tissues, modeling how tissues evolve in time. Thomas Sterling is in cyber physical systems and computer engineering, and his expertise is extreme scale, high performance hardware and software, where he's an international leader. Martin Swainier is in computer engineering, or also sort of cyber physical systems. He has embedded systems, network design. He's very famous for his network monitoring software and distributed data. So we advertised for positions starting, I guess, August 15th, a little out thereafter, and we got 184 applicants applied for faculty in ISE. And I was very excited by the enthusiasm for these faculty to join this new program, which is, they did not view the innovation as negative, they viewed it as positive. And we interviewed lots of potential faculty, and eventually 7 have accepted our offers to join the department. 5 of those are effectively joined today, August 1, and 2 will be joining in January of 2017. If you look at those 7 faculty, there's 1 in intelligence systems, the new faculty, 1 in computer engineering, 2 in bioengineering, who happen to be both coming in January, 2 in nanoengineering, and 1 in neuroengineering. Let's now go through the faculty. The first faculty is Li Jiang in computer engineering. He does high-performance computing, hardware studies, in particular memory. He has an undergraduate degree in computer science and a master's and PhD from Pittsburgh in computer engineering. He comes to us from AMD, obviously a major hardware company, where he's a senior design engineer. So Minji Kim reminds me that we really do not have 6 concentrations, we have 7. Because intelligence systems itself is an area which students can graduate in at the PhD level. That just means you get a degree in intelligence systems engineering without any specific concentration. And I pointed out how central the concept of an intelligent system and the converting of data into knowledge and wisdom was. So he has a background in signal processing. He actually has an undergraduate and master's in computer engineering, and he does machine learning for multimedia. He has a PhD from computer science from University of Illinois at Urbana-Champaign. Vikram Jadeo is in nanoengineering, and he uses high-performance computing simulation to study new materials. He's already working with the chemistry department on material science ideas and new proposals. He has a physics degree from So ending up with a PhD from, again, UIUC, Urbana-Champaign. And he is, a postdoc at two well-known material science departments, Northwestern and Johns Hopkins University. Alexander Gumenik is pretty exciting. He is in a rather different type of work, whereas both Vikram and Alexander are in nanoengineering. Vikram is doing simulation, and Alexander's building things. Namely, he's building intelligent fibers, and he's using 3D printing to build these things. And he has a physics and math as an undergraduate, an applied physics and master's and PhD from Hebrew University. And he comes to us from a postdoc at MIT's Department of Materials Science and Engineering, and he is in a 3D printing startup, which he's just left, called Formlabs. And in fact, if you go to the Crest building in Walnut, you will find a Formlabs 3D printer there. That was quite coincidental. They're just a leading startup in this area. And so if we look at what we have here, we have a pretty broad range from hardware, building intelligent systems, simulating materials, and then using materials to build things. The final three faculty, Eleftherios Garifaldilis is in neuroengineering, and he is pretty exciting in that he is building open source software for MRI imaging. So he will work closely with psychology and brain science who use MRIs extensively in their research. And he is a pioneer in actually the open source concept. He has lots of people around the world working on his software. His undergraduate degree is in computer science. His master's is in brain and mind science, and a PhD in cognition and brain science from Cambridge University, England. Maria Bonderson-Bolin is in bioengineering. She's joining us in January. And she is studying toxicity, which is, of course, a very important area. We need to understand how the environment is getting affected by these various toxic contaminants, and avoid what happened in Flint and places like that. So she is an expert in systems biology and computational toxicology and experimental imaging. She will have a major imaging apparatus as part of her startup. Her undergraduate degree is in biology and a PhD from Sweden. Currently, she is at the University of Houston. And the last faculty, whose name is secret, he's accepted but doesn't want his name to be generally known. He does modeling and data analysis in the medical area. All right, good. This is pretty exciting, but unfortunately, if you have a curricula, you need some courses. So if you look at all those courses and which we discussed for cyber physical systems and computer engineering at the graduate and the undergraduate level, well, maybe we can get away with not so many at the PhDs, but the master's students will need plenty of courses. Remember, they all have to take 10 courses and multiple areas. And the undergraduates, we have at least 2 tracks and 2 possible additional concentrations. So my estimate is we have to construct around 50 new courses in 4 years. So 4 years is when the end of which the first undergraduate will have graduated, so they'll have taken all our classes. And also we'll have PhD students, of course, some of which probably will have graduated, almost certainly. And we'll have the master's program will have run its 2 years for the first students. So that if you add it all up, it's about 50 new courses. However, we're also ordered and want desperately to make our faculty the very best in research. So there's a sort of tension here, where they all have to write NSF career proposals, hopefully the end of their first year. And we also need these courses, sort of at least some of them now, before we've got enough faculty. And so we've made a sort of plan to try to address all of this, which is actually sort of illustrated by this presentation I'm doing here. I'm a firm believer that you can actually at least reduce some of the effort for teaching by pre-recording all your video. Actually, for the 2 classes I taught last year, I have 70 hours of video, which I can reuse, most of it from year to year. And also I can, like this year, those videos are being used by somebody else to teach my courses while I focus on being department chair. So our plan is to use a mix of faculty and lecturers to prepare courses. The faculty will have a major role in designing and monitoring the course material. The lecturers will help a lot of the detailed preparation, and we're going to capture all these courses in video, maybe using, as I say, this video room we have here, and we will probably deploy it on what's called Open edX, which is the leading open source MOOC or online education technology. We're hiring people, both lecturers and a so-called director of curriculum. I'm interviewing those people in the next couple of weeks. So the idea is the faculty will spend more time designing and less time delivering, but still the students will get a high quality education. So as part of, I already mentioned this concept of the collaboratory. I'm not certain Bill Wolfe invented this, but he popularized it in my community, which is in collaborative is an environment where participants make use of computing and communication technologies to access shared instruments and data and to communicate with others. So that reminds me, we're going to take all the instruments that ISE faculty use, the microscopes and the MRI devices, and try to connect them with modern technology, modern streaming data technology, to the back-end clouds for their data analysis. We also want to have people communicate, so we're going to get the very best possible collaborative technologies in the ISE buildings. And we're going to think of ISE as a department, which is the faculty and students, and a collaboratory, which are the partners. And we have currently very wonderful liaisons with parts of the campus. Those will be now thought of as part of the collaboratory. And we have, for instance, many departments on the campus. I mentioned several of them already, but also, for instance, speech and hearing science is very interested in working with ISE. Most importantly, for sort of engineering, we have to involve industry. And so we'll have an industry consortium and then the Crane liaison. I mentioned already the important Navy base in Crane, south of Bloomington. And they will all be part of the collaboratory. So I'm hoping to hire somebody to set up this collaboratory and organize all this over the next few months. And the collaboratory, which will have, say, faculty from around the campus and organizations, and particular an industry advisory board, they'll have a strong role in advising the department on all sorts of things. And in general, I'm sure the collaboratory will grow faster than the department. And it will also be a natural home for things like the Grand Challenge projects, which Indiana is setting up, because those will all be collaborative with other faculty outside the department. We will also try to take this concept and put it into a proposal to NSF to set up what's called an IUCRC program, which is NSF's industry interaction program, which is particularly strongly involved with engineering. It has some computer science involvement, but it's mainly engineering, which suits very well ISE. And the final slide is actually things we have to do. There was a wonderful Blue Ribbon Committee which met in early 2015 to advise the president on how engineering should be set up, and it said master's degrees are very important. So we didn't do that. That's unfortunate. We have to work on that. The undergraduate curriculum should include a non-school option. Well, we didn't do that yet, so it's on our list of things to do. We need a visiting committee. That's sort of our collaboratory. And then it points out that we need lots of startup and new faculty. And I'm pleased to say the university has stepped up to this type of startup for all the faculty with major experimental facilities. And so I think we can deliver on this message. So here we are. Intelligent Systems Engineering is set up. We have founding faculty, we have new faculty, we have new undergraduates, we have new graduate students. We'll have new programs coming along, and we expect to make a real impact, because this is the way, an interesting approach to engineering, which has significant advantages over previous more established approaches. So thank you very much, and I hope you can help us deliver on the promise of intelligent systems engineering.